beam deflection example, which is says we have a simply supported beam that is subjected to a distributed load. Q of x is omega naught sine of pi over x pi times x divided by L. And they've already derived the expression from that to get us to that. When that's true, that the deflection y follows that function there. I'm not even going to repeat it, but you can see it there on the screen. And it wants us to determine the expressions for the slope, which is theta, the moment, which is m, and the shear stress, or the shear, which is v. And we're going to take each one of those and work those out. So again, let's set up what our picture looks like. We've got a simply supported beam, so it's just on each end. We go from 0 to L in the x direction. Y is going to be the deflection, how much is pushed down. And our distributed load is actually a sine function, so it looks something like that maybe. We could do a little bit smarter about it and figure out, with the period and those sorts of things, how many times it actually would repeat on the length of the beam. But essentially, what we have is this. And so we're, again, asked to find the slope, the moment, and the shear. So the key things we need to remember back from that, we know that, given our first equation, we know that slope is the derivative with respect to y. So it's the first derivative. So we're going to take our constant, stays out front. We just have to take the derivative of sine. When we take derivative of sine of something times x, we get that, which we're multiplying by x, so pi over L. And the function changed from sine to cosine of that same expression inside. So we could simplify that a little bit and get that the slope function is, we could cancel a pi, we could cancel an L, so negative omega L cubed over pi cubed EI times cosine of pi over L times x. So that's our first answer. Our second question asks us to find the moment. And if we remember back from our discussion before, we remember the moment is EI times the second derivative of our deflection. Or the other way of thinking of that is EI times the derivative of our slope. So if we have our slope expression, we have EI. We can simplify that. EI, m of x is EI times, we're going to take the derivative of this, so we're going to keep the constant out front. Taking the derivative of cosine, what happens when we take the derivative of cosine? We get this coefficient comes out. It turns into negative sine of what's inside. So that would be our derivative of theta. And then we can simplify that again. So when we simplify that, the EI's would cancel, one on top, one on bottom. We could cancel a pi, we could cancel an L, negative omega, and the negative over here would cancel. So we're just left with omega naught, an L squared, a pi squared, and then our expression sine of pi x. Sine pi over L times x. Alright, so the next goal is to find the shear. And again, if we remember back to our previous work, we know that the shear is EI times the third derivative. Or that's the same thing as saying the derivative of m of x. Because it would just be taking this and going one more step. So we can do that. So if we take that derivative, we would keep the constant out front. Theta naught L squared pi squared. Taking the derivative of sine, again, coefficient comes out front, it switches back to cosine. We simplify again, we can cancel another L, cancel another pi. We end up with omega naught L over pi times cosine of pi over L times x. And that was the last expression we were asked to find, is to get the shear. But if we remember back from when we learned this, we remember that to get the distributed load is the same as negative EI times the force derivative of y. Or another way of saying that is it's negative the derivative of v of x. And writing that as 4 tick marks is starting to get out of hand, but what's done is done. So we could do it one more time and just see if we've got the right expression back. So let's do that. So if we took q of x, I'm going to start by putting in a negative sign, and then I'm going to take the derivative of this. So we'll keep the constant. When I take derivative of cosine, I get negative this coefficient, and it becomes sine So again, let's simplify it one last time. Pi's cancel, L's cancel, negative, negative. So I just end up with omega naught. I end up with sine and end up with pi over L times x. So if I go all the way back, I get the same equation that they started with to give me deflection. So really nice to see it come full circle, and gives us a lot more confidence that these answers along the way were probably right.